Not so many years ago, perhaps 5 or 10, it was thought that certain AI applications would take much longer to develop. However, thanks to a series of technical innovations, we've reached this point more quickly than expected. First, mathematical adjustments in neural networks have substantially improved their performance. Second, machines have advanced considerably, allowing us to leverage their computing power. To understand how far we've come, let's look at some examples of what can be done with AI today. One interesting case is identifying small objects in images and videos in real time. For instance, here's a clip from the Stanford Drone Dataset, which contains images and videos of different types of objects, including pedestrians, cyclists, skateboarders, cars, buses, and golf carts within the university campus. We also have tools like Google Translate offering real-time text recognition and automatic translation. So by simply pointing our camera at foreign text, we can instantly see the translation in the desired language, making it easier to navigate unknown environments. Another common example is the ability to remove an object from an image and then either replace it with a different one or fill in the background coherently based on the given visual context. But it's not just about images. AI can also be applied to the analysis of signals, such as those coming from IoT sensors, financial data, or text. For example, some models can analyze text to determine its overall sentiment, identify emotions, and extract mentioned categories. Despite how good these applications may seem, it's important to note that the specific techniques used to generate them only work if implemented properly. That is, the effectiveness of AI models and the usefulness of the systems we build depend on our ability to design and operate them well. For instance, during the execution of a computer vision project, we might discover that our algorithm is labeling certain objects incorrectly. This could happen if the model has been trained on a set of images that did not include those specific items, leading it to confuse them with similar ones. To train a model, we need to provide it with examples of inputs and the corresponding outputs we want it to generate. This process requires meticulous manual annotation. Therefore, the people who perform this task must receive very specific instructions based on the desired applications. Another factor to consider is the amount of data required for training. It is difficult to determine this beforehand, so an experimental approach is usually recommended. We can start with a manageable quantity, train the model, and evaluate its performance. For example, we might begin with 100 images, label them, and generate our detection model. Then, if it does not achieve the desired performance, we should acquire and tag more images until an adequate level of precision is reached. Our final example is a model that takes an image as input and generates a caption for it. This type of system combines the fields of computer vision and natural language processing. By analyzing the visual content of an image, it identifies objects, actions, and context to construct a coherent and relevant text description. If a model of this kind wrongly and repetitively assigns certain labels, we might have overtrained it with images that included many such elements. The problem here lies with the dataset design. Maybe our training data contained numerous bicycles, which led to the over-identification of these. That's why it's critical to design well-balanced and representative datasets according to the context in which the model will be applied. These examples demonstrate how AI advancements are expanding our possibilities and highlight the importance of dataset design for model performance. Accurate labeling and data variety are essential to achieving precise and useful results tailored to the specific requirements of our applications.